about a semiconductor? Okay. Well, a semiconductor is a metalloid with electrical conductivity between that of metal and an insulator, and it can be chemically altered to increase its conductivity by adding a dopant. Okay, so what does all of that mean? Well, for one, here we notice this is pure silicone. Okay, so here would be its valence band, which would be in the 1s, 2s, 2p, 3s. That would be the 3p level. And so its conduction band is the very next level up, which would be 4s. And there's a big gap between that. And that gap for silicone corresponds to 107 kilojoules per mole. That's a lot of energy. That's so much energy, in fact, that pure silicone on its own is not a good conductor. Okay? So what that means is something needs to be added to this silicone to bring that conduction band and valence band down to each other, to make that what we call band gap. So that's the band gap. We want to make that lower. And as it turns out, we don't have to make it so that they're touching. We can still have it so that there's a tiny gap that will require an input of energy. But what we want to be able to do as good and smart engineers is tailor that material so that I can have the band gap be an exact amount of energy that I want. Something like, equivalent to a battery power or some type of power that I can put into the material and induce conduction. Okay. So reminder, here's what all of our metalloids. So it's the stair step. Okay. And most notably, silicone is by far our most important semiconductor. And this is where the Bay Area gets the name Silicon Valley. I don't know if you knew this or not. Many of you are from this area. But that area, right, Palo Alto and San Jose and all of those areas, it's referred to as Silicon Valley because that's where all these semiconductors were created. Okay, that's where this revolution took off in the late 70s and early 80s that gave us the modern computer. Okay, so let's keep going. So how do we tune our semiconductor? Well, we've got two scenarios here. I've got silicone doped with phosphorus. And by saying silicone doped with phosphorus, it's kind of like making an alloy out of it, right? We're mixing a little bit of phosphorus into the empty holes of the silicone lattice, all right? And so now, once again, here's my pure silicone with a 107 kilojoule band gap, okay? So now this picture right here, let me box this off. This is my silicone mixed with a little bit of phosphorus. And so here I have my silicone valence band and I have my silicone conduction band. But now, if you notice here, because phosphorus is one more element over, we've added one more electron. So that's silicone 3p. So now this purple right here is phosphorus 3p. And you notice if we zoom in, it's got a much smaller band gap. Okay, so the band gap for a silicone doped with phosphorus is only 4 kilojoules per mole. That's tiny. That's much, much tinier than the 107. And so as a result, we would call this an N-type semiconductor. And N stands for negative because we're adding phosphorus, which has more electrons than silicone. So we're making this thing more negative overall, or we're adding more electrons overall. But the result is we have greatly reduced our band gap, which is really cool. Okay, so we can make another type of semiconductor, and this type is called a P-type. Okay, and so if we now look at this p-type here, so once again, this purple, this is my silicon valence band. This is my silicon conduction band with that really large 107 kilojoule per mole. But now if we look at gallium, so gallium, it's down one position, but it's over to the left, so that means it has less valence electrons than phosphorus. And so the P stands for positive. And now it's the same scenario. You can see now here is my empty gallium conduction band. So this would actually be like the gallium 5s. And you can see if I zoom way in, it has a much, much smaller band gap than the silicone on its own. Okay. So what is that useful for? Well, again, so here I have some just some summaries of all that stuff I just said. An N-type semiconductor, semiconductor containing an electron-rich dopant. A P-type semiconductor, a semiconductor containing electron-poor dopant atoms. Well, now what this thing can be used for is one example, a solar panel. Okay, so this is useful as a solar panel because now we recognize that we do have to put energy in to get these electrons to migrate from the valence band to the conduction band so those electrons can flow. But now with this much, much smaller band gap, we don't have to have a whole lot of energy to induce that to happen. So this is really cool. So that means as one application of a semiconductor, we could shine light on it. That light contains enough energy to promote electrons to flow through the conduction band, and then we can produce electricity. Another way this is really useful is we can make LED, light emitting devices, doing the opposite. So in other words, if I pump some electricity into my conduction band, so for example, let's say I pump electricity into my gallium conduction band, well now those electrons want to release energy and go back down to the valence state, and when they do that, they emit light as a result. And so what's very cool, not only is this incredibly efficient, right? LEDs last for years and years and years, but by carefully engineering these semiconductors to have a certain band gap, you can tune the light output that's created. Very cool. So all of those like really fancy, sophisticated, color changing lights that you see, those are all LEDs and they're made up of semiconductors. Another application of a semiconductor is a remote control, right? When I point my TV remote control at the television, that thing has a receiver in it that contains a semiconductor that has been programmed to match the frequency of the remote. The remote, emits light or radio frequencies. Mostly it's infrared, but some do emit radio frequencies. And some engineer has engineered a sensor to have a band gap that has the same energy as the remote. So when you push that remote, it responds immediately, pumps an electron into the conduction band, and causes the TV to turn on. So very cool. So there are semiconductors in every single piece of electronic we use right now. And they have become incredibly useful for modern life. And as you might have guessed, graphene, right? This is the next amazing material for our consumer electronics. Okay, folks, that's it on solids.